Okay, so we were talking about the breakdown voltages in a bipolar junction transistor. So we have two breakdown voltage we discussed yesterday. One is BVCBO, that is the breakdown voltage of collector based junction when the emitter is open, and and the BVCEO, that is the breakdown voltage of the collector emitter junction, collector emitter when the base is open, right? So these are the two important breakdown voltages in a bipolar junction transistor, that is BVCBO and BVCEO. So so basically, I mean, so we'll discuss what is the source, means how the breakdown happens. So just before we start the discussion on breakdown voltage, so this just for your information, so BVCEO is always less than BVCBO, right? So when you are using, I mean, so when you are using bipolar junction transistor at a certain voltage, so you have to make sure that your voltage that you are applying, I mean, maximum voltage that you are applying, that should be less than the BPCO of your transistor. Okay. Um, so basically, so let's start about talk about BPCBO. So collector based junction is a reverse biased junction, right? Because in the typical operation of a bipolar junction transistor, your collector base is reverse biased, right? and if you look at the doping on both sides of the junction, so one side I have base doping, and other side I have collector doping. Base doping and collector doping, they are not very high doping, right? So typically the avalanche multiplication happens, and the breakdown is mostly because of avalanche breakdown, right? So we had discussed about breakdown in the PN junction. I have just pulled those sheets here. um, so if you think of it, means if you recall what you have discussed in the PN junction, right? So the PN junction, so basically I have like if I apply some voltage, if I apply some reverse voltage across this junction, so whether you apply reverse voltage or or you have not applied any reverse voltage, so electric field always peaks at the junction, at the metallurgical junction, right? So so this the maximum electric field that we had derived earlier, so EM, maximum electric field, which is at the metallurgical junction, is nothing but Q times ND times Xn divided by epsilon, which is equal. So basically, both side we have depletion charges. Both the depletion charges are equal. So electric field is charged by epsilon. So this is Q ND Xn by epsilon or Q N XP by epsilon, right? And we had also discussed, we had also derived Xn and Xp. I am just taking this here. So so here it is reverse biased. So when you apply reverse bias across a junction, the voltage drop in the junction is previously there is a voltage drop which is VBI, and VBI, we know the value of VBI, which depends on the doping on both the sides. But when you apply reverse voltage, the voltage drop across the junction is VBI plus applied voltage, right? Because your voltage drop increases, right? When you forward bias, your voltage drop across the junction decreases, right? That will be VBI minus applied voltage, right? But we are applying reverse voltage, so your voltage drop across the junction is VBI plus applied voltage. So we had derived this depletion region in the N side, depletion region in the P side. I'll just not go to that now, but I'll just, so if you look at these things, so your Xn and XP depends on the doping, right? Okay, so from here, if you use this in these equations, right, so I could write down the field, the maximum field, right, the field, right, the field at the metallurgical junction, in this way, right? So here I had done NB and C because see so NB is the base doping, the doping in the base side, the base doping, and NC is the collector doping, right? Collector doping, right? So, so here the assumption is NB and NC are constant in the base and collector, right? So if you, I mean, so your electric field, the electric field, maximum electric field, which is at the metallurgical junction, I could write it by this formula, right? Okay. So here so as you go on increasing the applied voltage, so if you go on increasing the applied voltage, that is means applied reverse voltage across this junction, your maximum field across junction will increase, right? And junction will break if the maximum field is more than critical electric field, right? So every material, right, has a critical electric field, right? And silicon also has a critical electric field. So if your maximum field across the junction is more than the critical electric field, then the junction will break. And this breakdown is mostly because of avalanche, right? Avalanche multiplication. And we had discussed avalanche multiplication. I'll just quickly go through the avalanche multiplication. Um, so, okay, so um, so here also we could take this. So this is my maximum electric field, right? So the critical electric field, I mean, because as I told you, right, if maximum electric field reaches critical electric field, your junction will break, right? So I could find critical electric field just by replacing the applied voltage by VBR. So when the applied voltage reaches breakdown voltage, that means the field is critical electric field, right? Right. So so here means I could write VBI plus VBR equal to VBR because your built-in potential is hardly 0.8, 0.9 volt, right? And your breakdown voltage that we're talking about of a junction, right? It is around 4 to 5 volt, even 10 volt in some cases, right? So your VBI plus VBR, I could always approximate it as VBR, right? So if I do that, then I could write the critical electric field is nothing but this formula here, right? Right. And your VBR I could write down by this, right? So your breakdown voltage is nothing but epsilon times E critical square divided by 2Q into 1 by NB plus 1 by NC, right? So breakdown, this is the formula for the breakdown voltage, right? Right. And the breakdown voltage, because see, basically if you see, means we have done our means we have learned how to design a bipolar junction transistor, and we know that your collector voltage, your collector means your base voltage is always more than, sorry, base, not base voltage, the base doping is always more than collector doping, right? So if I take this assumption, but it's not always true, right? It depends, right? So let's say your NC is less than NB, right? In many cases, I mean, in the common case, your NC is less than NB, right? Your collector doping is less than the base doping, right? If that is the case, then your breakdown voltage will depend on the collector doping, right? So this is typically the case. So if I want to design the BVCBO, that collector base breakdown voltage of your bipolar junction transistor, that means I have to play with the collector doping, right? If I want to have higher BVCBO, that means my collector doping needs to be lower, right? So because base doping, if you play with base doping, so base doping is a very sensitive parameter, right? Right? Because base doping will decide your current, but collector doping does not decide your current, right? So here, so if you want to change the breakdown voltage of the device, you cannot really change the base doping. If you change the base doping, what will happen? Your current will change, right? Which you do not want, right? So at a fixed current level, current carrying capacity or current, right, you could change the breakdown voltage by changing the collector doping, right? That's the reason collector doping is optimized to move the breakdown voltage, right? To change the breakdown voltage. So as I told you, the critical electric field for silicon means critical electric field varies slightly with the doping concentration. So critical electric field little bit changes with the doping concentration. For silicon, the critical electric field is in the order of 0.3 megavolt per centimeter to 1 megavolt per centimeter, right? Right. So if your field in the junction goes beyond this number, then your junction will break, right? So this is for silicon, right? And if you go to germanium, right, germanium has a lower band gap, right? So that lower band gap means the critical electric field will be even lower, and uh, you'll have means breakdown voltage. You'll have lower breakdown voltage, right? And similarly, the critical electric field mostly depends on the band gap. Higher the band gap, higher the critical electric field, right? So this is that's the reason, means if you want to means if you want to build a bipolar junction transistor which operates at very high voltage, right? Then you have to go for material which has a higher breakdown voltage, right? And typically people go for gallium arsenide or even gallium indium arsenide. So basically materials with very high breakdown voltage. I mean higher critical electric field, so high breakdown voltage. Okay, so this is about BVCBO. Then talking about avalanche multiplication, because avalanche multiplication is because of the means. So if you think of means, just to recap what is avalanche multiplication. So I have again taken this PN junction example. Let's say we have a PN junction, and in the I am applying reverse bias across it. So there is an electric field from N side to P side, right, and that electric field increases with the application of this reverse voltage, right? So I have minority carriers in the P side, I have minority carriers in the N side, right? So in the P side, I have Ni square Nb number of electrons. Let's say this is base, so I have Ni square by Nb number of electrons, right? And Ni square by Nc number of holes, right? Since I am assuming Nb greater than Nc, so let's focus on the holes, right? Ni square by Nb is much less than Ni square by Nc, right? So what happens? So I have electrons this side and I have holes this side, and I have electric field from N to P. So the electrons can travel because these electrons can drift from um, P to N, and holes can drift from N to P, right? So there is a reverse current, right? So that's the reverse saturation current in your typical PN junction, right? And this reverse saturation current is because of both electrons and holes, right? But since in our case, when we're talking about our typical bipolar junction transistor, where Nb, your base doping, Nb is higher than Ns, right? So your Nb is higher than Ns. So mostly reverse saturation current is because of holes traveling from N side to P side. That means collector to base, right? Okay. All right. So what happens? I mean, so if you recall the things, so let's say I am talking about holes moving from collector to collector to base. So the holes, because the holes when they're moving, please recall the holes have high energy. So if I'm this is my valence band, the whole energy increases as you go below the valence band, right? So whole energy is minimum at the valence band, at the top of valence band. So here the whole energy is minimum, and the energy of the holes will increase as it goes below the valence band, right? So here, let's say this hole is traveling from N side to P side. That means this has lot of energy, right? So basically, this has this much energy, right? Which is the Q times applied voltage. I mean, this plus VBI, right? Right. So then, right. So here, uh, right. So this hole is, I mean, this has some energy, so it could lose, and it could go to, it could lose some energy, right? So it could lose some energy. Lose means, see, it doesn't lose energy, right? It's a conservation of momentum, right? So basically, if a hole has very high energy, it could give some energy to the electrons, right? Or some energy to the holes, right? So basically, right? So in this case here, the hole is interacting with the electron in the valence band, so it will give its energy to the electron. So electrons, by getting that energy, can go to the conduction band, right? So when the electron go to the conduction band, it leave behind an electron and another hole. So at this point I had a hole. Now that hole gives an energy to electron. Electron goes to conduction band, it leaves another hole, right? That in the process I have two holes now, right? So these two holes will again, because I have electric field, so these two holes will again move. So they have a particular kinetic energy, right? So they can always lose energy, right? So in this case, they will lose energy, give two electrons. So the two electrons will go to the conduction band and another two holes will generate. This is how it multiplies, right? Right. So from one hole to two hole to four hole to eight hole, 16 holes means the number of holes and number of electrons will increase, right? So this is multiplication, right? This is avalanche multiplication that we had discussed earlier also, right? So the breakdown will happen when this multiplication factor becomes infinite, right? The number of electrons holes will increase, but if that's somehow this electron holes becomes infinite, right? Number of electron holes becomes very high. That means you have very high current flowing across the junction, and we call it breakdown, right? So the multiplication factor in this case, I could write down that. So this is the equation that we had also uh, used in the PN junction. So this multiplication factor in this case is 1 divided by 1 minus VCB by BBCBO to the power m. So here you could see when VCB, the collector base junction, collector base VCB, the voltage across the collector base is equal to BBCBO, then your m becomes infinite, right? Right. So this is the breakdown, right? So here you could see, right? So as you go on increasing your VCB, that means you are increasing the reverse voltage across the collector base junction. At some point, the multiplication factor becomes infinite. So your increases, right? So this is see, if you look at this characteristic here, right? If you look at this characteristic, so look at this characteristic, it is flat. Let's say your VB is 0, so it is flat and it's increasing suddenly, right? But in a typically what happens basically what happens is, so there is a slight increase because your multiplication is happening, so electron hole pairs are increasing, so basically you will see a slight increase, right? You will have um, you'll have, there is a finite slope, right? All right, and this so basically, because even if at any point your multiplication is happening, right, slowly your current is increasing, at some point it shoots up, means because multiplication factor becomes very high, so electron means current increases, right, drastically, right? And okay, so this is the BBCBO, right? BBCBO means breakdown voltage at the collector base junction is because of avalanche, multiplication, right? Okay, again, so basically now also you could see, if I forward bias, right? So right, let me use this. So here. Okay, so let's say my emitter is grounded, so I am giving voltage to VC, right? And if base is ground, base is open, basically, um, right? So BBCBO is defined when the emitter is open, right? That is fine, right? The emitter is open, and I am giving some. So your, let's say if you want to measure, you means in the lab, you will keep the emitter open. You'll keep the emitter open. You will put the base to ground, then you give some VC. At some point, it will break, right? So this is BBCBO. That is when the emitter is open, right? But you could also give some voltage. Let's say emitter is not open. Means emitter is connected to ground, and you could give some voltage here, BV, right? Let's say I give zero point 0.1 volt. That means I am forward biasing the emitter base junction by zero point 0.1 volt, right? That means I am injecting some electrons, right? Right. So then if we go on increasing VC, right? So I am injecting some electrons, that electrons are reaching, and these electrons are going through the junction also, right? So these electrons also, because I told you, right, BBCBO is because of magnetic carriers going from N to P or P to N, right? But in this case, right, the electrons will have a role to play, the electrons that has been injected from emitter to base, because when they're going through this junction, they could also create impact ionization, right? Right. So As you go on increasing your, means as you forward bias more and more this emitter based junction, you will see the breakdown voltage will reduce because you have lot of electrons, means you have some electrons actually, right? So you are injecting already some electrons, and these electrons can gain energy and start impact ionization, right? So these electrons will act as a precursor to the impact ionization process, right? Um, so your breakdown voltage, as you go on increasing your VBE, you will see that your breakdown voltage will reduce little bit, right? But that is not BBCBO. BBCBO by definition, BBCBO is when your emitter is open, right? But BBCB, the breakdown voltage between collector base junction will decrease as you go on increasing the BBE at fixed, means okay, right? So let's say, right? Let's could state it like, right. So breakdown voltage between collector base junction, breakdown voltage of collector base junction will reduce when you increase the VB, right? But BBCBO is where your VB, you are not, means basically when the emitter is open, that means the emitter is open means your IB is zero mostly, right? Your base current is zero, right? VB emitter is open means you are not injecting anything, right? That means your base current is also zero, right? Okay. So any questions here? So if you want to increase BBCBO, you have to play with NC. So by changing the doping, collector doping, you could change the BBCBO values, right? So this is how typically done. So the collector doping is typically used to tune the breakdown voltage of your transistor, right? So if you want to operate your bipolar junction transistor at higher voltage, right, then you make sure that your collector doping is lower, right? But we also observe, right, if the collector doping is low, we'll have cork effect, right? And we have other effects will also, secondary effects will come into picture. Okay. Um, okay. So this is BVCBO, and then we'll go to BBCEO, right? See, BBCEO is an interesting concept because see, basically why BBCBO, we are talking about BBCBO because when you're operating in the common emitter configuration, the output voltage is VCE, right? So output voltage is VCE, and so you see how, means basically we want to see how much maximum output voltage that you could give, right? That's why the BBCO is important, right? So BBCO is your base is open. That means, so you could think of that you are sorting the emitter, base is open, then you are applying a uh, voltage at collector, right? You go on increasing VC, you go on increasing VC, and you see at what point your current, like you have IC, right? So basically, this is your IC current and IE current, right? Right. So you go on increasing your collector voltage. At some point, there will be high collector current flowing, right? That voltage is the your BBCO, right? But if you see, in this case, I could write down that because your collector, your base voltage is zero, your IC is mostly equal to IE because your base, your open, base is open, right? Okay. So, so let's start with, right? Let's say, I mean, let's assume that I am injecting some electrons here, right? Right. So I'll come to that point. So let's start that. Okay. So when I apply, means let's say uh, I am injecting. So let's start with this. Let's say I am injecting some electrons across the emitter base junction, right? So this will give a current, and let's say this current is Ix. Let's say any current Ix, right? So we have injecting some electrons across the emitter base junction. So that means to the base, right? So these electrons will diffuse. So when I apply, so these electrons will diffuse and reach the collector base junction, right? And I have a reverse volt, means because this junction is means I am applying VC, that means this junction is reverse biased, right? So there is a electric field uh, at the collector base junction which is from the N to P all the time, right? N to P, right? So this Ix is injected, right? Ix is because of electron is injected from emitter to base, and how many electrons reaching? That is nothing but alpha times Ix, right? The base transport factor, right? So basically, so the electrons that is reaching the collector base junction is alpha times Ix, right? Alpha times current, right? Base transport factor, right? Okay. So now these electrons, because these electrons um, will be injected because they will go through the junction, reverse bias junction, right? And they will impact analyze, right? So if you could write your collector current, see your collector current in this case is, so you have because let's say you are not injecting any current, that means I have a ICBO, I have ice, the collector base reverse saturation current ICBO flowing across the junction, right? Because ICBO is nothing but the holes are injected from N to P, because minority holes, because there is a reverse bias, there is electric field from N to P, so there are minority holes which is Ni square by Nc. So these holes are going from N to P, and there are some Ni square by Nb number of electrons which is going from P to N, right? So because of these two things, I have ICBO, right? So the total current flowing across the junction is alpha times Ix plus ICBO, right? And by multiplication factor, right? So this is my collector current, right? Because uh, I have some electron injected from emitter base junction, I have some electron hole flowing across the junction. So total collector current is because of both these things, right? Alpha Ix plus ICBO, and the IC I could write multiplication factor times this, right? Right. So what is happening here is, if you look at this junction here, so I have um, um, impact transition happening in this junction, at this junction, because this is the reverse bias junction, impact transition is happening. So when the impact transition is happening, that means I am generating electron hole pairs here. I am generating electron hole pairs in this at the collector base junction. And when I'm generating electron hole pairs, these electrons, because I have a field from N to P, the electrons will always go from this side, right? And holes will go to the substrate, right? Sorry, base, right? Holes will go to the base, right? And these holes have nowhere to go, so they are just accumulated in the base, right? The moment the holes are accumulated in the base, that means I'm increasing the potential of the base, right? So because of the holes accumulation, I'm increasing the potential at the base, right? Base potential increases. So the moment base potential increases, that means I am also forward, means base potential increases means I am forward biasing this junction more and more, right? This junction is forward biased, right? Right. This junction is forward biased. That means I'm injecting more electrons now in the across the emitter base junction. That means the impact transition will be again increase, right? And you have more electron hole pairs generated. Holes will again come to the base, so they have nowhere to go. So they'll be collected at the base, and they will increase the potential of the base, right? Again, that means your emitter base junction will be more and more forward biased, right? So this is a positive feedback loop, right? So if you see, this is a positive feedback loop. So at some point of time, your current will be very high. Your collector current will be very high. That means your emitter current will also be very high, because collector current equal to emitter current in this case, right? Right. And that point we call the breakdown. So here in this case, this is a BBCEO. That means no, see, there is no junction between collector emitter, right? But I call it collector emitter because this is the breakdown voltage, because at some collector emitter voltage, right, high current is, means my transistor is means high current flows across the transistor, right? That voltage I call it BBCO, because my base is open, right? So at the breakdown voltage, then my right, so I see basically at the breakdown, uh, then my current means this current will be ICO, right? Whatever current is flowing during the breakdown, then this is nothing but M times alpha times ICO plus ICBO, right? Right. So here I could also write your ICO is M times ICBO divided 1 minus M alpha, right? So see now, if your M alpha becomes 1, right, then your ICO will be infinite. That means very high current flow. But this is unlike your this is unlike your BBCBO. BBCBO, what are telling, right? So your M becomes 1, right? So basically, at breakdown voltage, right, your M, okay, your M becomes very high, right? Okay, so let's not confuse you. So, but if you see here, so when your M alpha becomes 1, that means your very high current will flow, right? So here that means M alpha is becoming 1, right? So, but there in the, when we're discussing about BBCBO, we are talking about when your multiplication factor becomes infinite. We are not talking about infinite here, right? Just when M into alpha becomes 1, your BBCBO will means your junction will not means high current will flow across the transistor, right? So again, if I write M, I have right. So M, I could write down. So M alpha equal to 1, right? So M I could write down. M is nothing but I had defined M earlier. So M is nothing but 1 minus VCO. Um, M times alpha becomes 1. See here, why I have written like this, right? So when we are applying BCE, right? So when I am writing BCE, so BCE is nothing but BCB, right? Um, BCB plus BBE, right? Your BCE, your collective emitter voltage is nothing but BCB plus BBE, right? So how is that? So let's say, right? So I could, so this is your VC, right? And this is your VCB, and this is your VB, right? So I could go from collector to emitter through this path, right? That means your VC. I could go also, so I could write VCE is nothing but, because if I see this voltage is nothing but VCB plus VB also, right? But if you compare, I mean, when you're talking about reverse bias junction, right? So you, when you're talking about breakdown, your VB, see, we have seen, right? Your base to emitter voltage, I mean, cannot be very high, because base to emitter voltage will be hardly 0.7, zero point 0.8 volt, right? Right? So your VB is always less than VCB. So VCE, when you're talking about breakdown voltage, I am talking about VC. Okay, so here, let me write down like this, right? So I could write down on the breakdown. So VCO is nothing but VCBO plus VB, right? But VB is much less. So I could write, not VBCBO, right? I just made some mistake. So your VCEO, so there will be some VCB at which the your um, there will be some collector voltage at which my VCO happens, right? That means at some collector voltage in this case. So as I go on increasing collector voltage, so at some point your IC becomes very large. Your IC or IE becomes very large, right? That is my VCO point. So VCO point is VCB plus VB. but that voltage is definitely more than VB, because VB is around 0.7 to 0.8 volt. So I could write down your VCEO is nothing but VCB approximately, right? So if I do that, and I know um, my M, the multiplication factor here I have defined, right? 1 by 1 minus VCB by VCBO to the power n, right? So I could also write this as, in this case, 1 by VCEO by VCBO in this condition, right? Right. Okay. If I do that, then my M into alpha becomes 1 for VCO. So if I do that, then this will becomes 1, right? So here you could write down 1 minus VCO by BB. Basically, this is based on VCBO, BBCBO to the power m equal to alpha, right? Um, so 1 minus BPCO by BPCBO is alpha 1 by m, right? Um, so BBCO by BBCBO is 1 minus alpha, right? Okay, so no, I have done some mistakes on that. Sorry. Oh, yeah, that's the mistake, right? Yeah. So this is not whole square, right? 1 minus um, right? So this will become to the power whole times m equal to 1 minus alpha. 1 minus alpha is nothing but, you could write down 1 minus beta by beta plus 1. So this will be beta plus 1 minus beta by beta plus 1, right? So this is 1 by beta plus 1, which is nothing but 1 by beta, right? Right? Okay. So here you could see your BBCO is BBCO to the power m is BBCPO to the power m divided by beta, right? And your BBCO, breakdown voltage of BBCO, is nothing but BBCBO by beta per 1 by m, right? So here, okay, so this is just a formula, right? So your BBCO is always less than BBCBO, right? So the relationship is your BBCO is BBCBO divided by beta times 1 by m, and m is nothing but 3 to 6, right? M is, we 3 to 6. Let's say if m is, let's say m is 4, right? If your beta is 100, so your BBCO will be BBCBO divided by 100 or fourth root, right? So basically, right? So this will be root over 10, right? So root over 10 will be around 3. So this will be BBCBO by almost, right, by 3, right? So or 3.3 or something, right? Okay. So you see your BBCBO, if you have designed your transistor for a particular BBCBO, and BBCBO is nothing but the breakdown voltage of the collector base junction, as I told you, that it could change by changing the collector doping, right? And your BBCO will be BBCBO, whatever BBCBO that you have designed, divided by 3.3 volt, right? So if you have designed your BBC, so let's say you want to operate your VCC, your VCC is at 5 volt, that means your BBCO should be more than 5 volt, right? So so for example, so if you want your transistor to operate at 5 volt, then your breakdown volt BBCO should be more than 5 volt. Let's say it should be 6 volt, but your BBCBO should be 6 volt times 3.33, which is nothing but almost 20 volt, right? Right. So so for a 5 volt operation, then you have to design your transistor such that BBCO becomes 20 volt, right? So this is how you have to. So then if you know, okay, BBCO should be 20 volt, then you will choose your NC, your collector doping accordingly, right? Collector doping and collector length of the thickness of the collector accordingly, right? Okay. So this is how you, I mean, you design your transistors for breakdown voltage. As I told you, right, breakdown voltage are very important parameters of a transistor, which will give you what is the maximum voltage you could operate these transistors, right? And when you're talking about bipolar junction transistor, we have BBCBO and BBCEO, and BBCBO is nothing but the collector base junction. When you reverse bias the collector base junction, at what reverse voltage it will break, right? And that you could design by changing the collector doping, right? And your BBCO is lesser than BBCBO, so your VCC that you're operating, your operating voltage should be less than BBCO, right? So you see here, if you design a transistor for very high beta, right? So that's the reason very high beta is never preferred, right? You need a good enough beta around 80 to 100 is more than enough, right? Because if you go on increasing your beta, that means your BBCO will be very less, that means your operating voltage will drastically reduce, right? So you make sure that your beta is not very high. It's not required, you don't require very high beta, because very high beta will have other consequences, right? That means, see, you could also, I could also tell you, let's say your beta is very high, right? How will you make your beta very high? You will make your beta very high by reducing the base width, right? By reducing the base width, you'll make your beta very high. If you reduce the base width, right, then, I mean, so you're multiplying, because when you're reducing the base width, right, and you are injecting electrons and holes into the base, and hole is collected in the base, so the base potential is increasing. But if the base width is less, or base area is less, that means your potential will increase faster. That means your breakdown will happen faster, right, at a lower voltage, right? So this relates to this equation, right? See, this equation is just a model, right? But you have to understand how the breakdown happens inside the device, right? Okay, is it clear, BBCBO and BBCO, and why, how you have to choose BBCBOs for the normal operation of the device? Is it clear for all of you? If not,
Sir,
last question, huh?
sir, this equation, sir, the one seen ICEO equals to M alpha times ICEO. I didn't understand how this ICEO came here.
ICO is,
How how did we replace IX to ICEO?
because IX is the, see, if I IX is the current flowing, right? IE, right? So basically I started with this, right? So so let's say I am injecting some electrons from emitter to base, E number of electrons, right? And let's say electrons are injecting, right? And that electrons is giving my current IX, and this IX is IE. Is it right?
Yes, sir.
Right? So because your IE will be IX, right? In this case, because I am not considering the whole injection from base to emitter, right? I'm neglecting that part, right? So and your, and this IX, some part of this Ix is reaching collector, that is alpha times Ix is reaching collector, and the electrons flowing through, means basically the electron holes flowing through this junction is nothing but alpha times Ix plus ICBO, and which is responsible for the impact transition, right? So your collector current is M times alpha Ix plus ICBO. Is that part clear?
Yes, sir.
Okay.
But sir, also alpha, it should be alpha T, not alpha.
Yeah, alpha T. Yeah, you are right. Yeah, yeah, this is not alpha. This is alpha T. This is, I am telling base transport factor, right? So this is the base transport factor. You are exactly right. Alpha T, right? Okay. Don't um, yeah, but your I mean alpha. I mean basically your base transport factor. Okay. So now right. So see, okay. Um, Here I have taken some assumption. See, okay. Anyway, okay. Let's stick with this equation, right? I is equal to m times alpha t times Ix plus ICBO, right? So what I'm telling here is, so I have electrons holes moving in the collector phase junction, which is reverse bias, which is creating impact radiation, right? So because of this impact radiation, electron hole pairs are generated. Electrons go to the collector because the electric field is from collector to emitter. So electron will go to the collector and holes will come to the base. But these holes have nowhere to go, right? Because they are collected at the base. So once they are collected at the base, that means base potential will increase slowly because where my holes are being collected at the base, the base potential will increase, right? So the base potential increases. That means I'm again the means EB junction, um, the emitter to base junction is far biased, right? So emitter base junction is far biased means more electrons are more electrons injected, right? And at some point, this is a positive feedback process, right? Electron hole pairs are generated, holes are collected in the base. Because of the holes collected at the base, more electrons are injected. So then these electrons create impact transition, right? More impact transition, right? So this is a positive feedback process, right? So after some time, right, with this process happens after some time, very high current will flow, right? And so your Ix, so very high current will flow. Let's say that voltage at where very high current will flow. Let's say that is my BVCO, right? That is that voltage is BVCO, and the current flowing at that point is ICEO, right? So that's why I replace this alpha is Ix by ICEO here, right? Right, and my ICBO is still there, right? And the total current is nothing but m times alpha times ICO plus ICBO. So I could write this equation, right? So your IC, because IC is equal to IE, right? Because there is no base current. So your IC will also become ICO, your IE will also become ICO, and IE. So that's why I could write down ICO is m times alpha t times ICO plus ICBO, right? Is it clear, Om?
Yes, sir. And sir, if my holes are being collected in the base, wouldn't my alpha T decrease?
Your alpha t will decrease. Oh, yeah, yeah, but it means basically you're telling that when the electrons are traveling from the, means they will point, right? So alpha t will decrease. Why the alpha? Okay, so your base transport factor will decrease. You are right, but see the point is, uh, because the, see, even if with this base transport factor, right, alpha t, see, okay, you could, so you could, but the point is, the see, this also happens with VBE, right? Your when you increase your VBE, that means you're forward biasing your junction, right? Right. So your yeah, how can I explain this, right? So you are okay at this point. You are right. Your base transport factor will decrease, right? How much? How much it will decrease? Because you are injecting a lot of electrons, and your base width you have designed such that your base width is very small, right? Your alpha t, your base transport factor depends on the base width, right?
Yes,
Right.
sir.
So since you have already designed a very good transistor, your alpha t is very close to one, right? So you are assuming that okay, your alpha t is very close to one, right? So even if you are collecting holes, right? If even if you are collecting holes, since your base width is very low, so your alpha t will not degrade that much, right? That is the assumption, right? So basically, see, this is a model, right? So in the real case, in your device, definitely your alpha t will little bit reduce, right? So it will take more time for the breakdown voltage to happen, breakdown to happen, right? Because but in the model, when we're writing in the equation form, and we have taken some assumption that okay, alpha t is not decreasing that much, and alpha t is almost equal to alpha, right? Because uh, because here IB is not there, so IC equal to IE, because whatever electrons reaching collector current, they are collected, right? So your alpha t becomes alpha also, right? So that's the reason I have started with alpha, but that was my mistake. So alpha t is almost equal to alpha also in this case, right?
Yes, sir.
Yeah. So see the
Sir,
the point here is you don't have to see, this is just a model, right? And this is not a very accurate 100% accurate model, right? This just tells you that BVCO is less than BVCBO by this much factor, approximate factor, right? When you measure, you may get little bit deviation, right? But that is fine. So what it tells you that when your base is open, right? And when your emitter is open, when your emitter is open, you have a breakdown voltage, which is BVCBO, right? When your base is open, you have another breakdown voltage, which is BVCO. And if you think about the physics, right, your BVCO is will be smaller than BVCBO, right? Because your base is open, my holes are collected. Because of the holes are being collected, I am increasing the potential of the base, and that is forward biasing my emitter base junction, which is not happening in BVCBO case, right? When I'm talking about BVCBO, right, in this case, right, because my holes are not collected, holes are, see here, electron hole pairs are generated in this junction here also, but holes are but holes are collected by the base, because base is connected to ground, right? Your emitter is open, but base is connected to ground. So a base could drain out the holes from the I mean your base contact can drain out the holes from the base, right? Right, right? So base, the holes are not collected in this case, right? But when you go to BBCO, means when the base is open, right? When the base is open, holes are being injected, because electron hole pairs are generated, holes are being injected to the base, holes come to the base, but they are nowhere to go. So they are being collected at the base, right? So when they're collected at the base potential increases, and this is forward biasing your base emitter junction. And because of this forward bias, more electrons are injected, and these electrons help in the impact transition process. They help in impact transition process, more electron hole pairs generated, so it's a positive feedback process, right? Because of this positive feedback process, your BBCO is less than BBCBO, right? So you just have to keep that in mind, that you always think, okay, when I talk about BBCO, it will be a less number than BBCBO. But if I want to put it in the equation format, and this is not exact equation, you don't have to say that, okay, there is some, we have taken approximation, right? And if you go by the means equation, by taking several approximations, so we the BBCO is BBCBO by beta times 1 by m, right? So this is the number, right? Right. So the goal means the takeaway thing is you should understand why BBCO is less than BBCBO. And when you're choosing a power supply voltage, right? Let's say your transistor has to operate at this voltage, then that power supply that voltage should be less than BBCO, right? So when you're designing your bipolar junction transistor, so you should choose a BBCBO, because BBCBO will depend on NC. You should choose a collector doping to have a BBCBO, and based on the beta of the transistor, you'll get a BBCO, and your power supply voltage should be less than BBCO. Okay, is this part clear?
sir.
Yeah, Shruti, you had some question.
Yes, sir. So, like the question is a bit different. So, in power electronic course, we were told that if we have to use BJT as a switch, so we use it in like open base configuration. So we connect the circuit across the emitter and collector, and unless we inject current in the base, the BJT does not conduct. So it acts like an open switch, and when we inject current in the base, it works as a closed circuit. But here, like
Hmm.
even when the
See,
base is open.
when see, okay. So when in the BJT, I told you, right? So BJT, when we're using BJT as a switch, right? So BJT as switch operates in the saturation mode, right? That means you're injecting electrons from both the sides, right? So both the junctions are forward biased, right? So basically, when your transistor is off, right? Because when you tell, okay, the BJT is open, that means your emitter based junction and collector based junction is not forward bias, right? The moment you both the junction forward bias, you're injecting more of electrons, right? So you have two states, right? So one case you have a lot of electrons in the base, one case you do not have any electrons in the base. This is how you switch your BJT, right? Right? The BJT का problem है कि then when you go from on to off state, right? So you have to remove these electrons also suddenly, right? So it takes time, right? So it also takes some time to remove these electrons from the base, right? So there is a turn on turn off transient, right? Because you need time to remove these electrons, then you need time to put these electrons in the base, right? So but means why you have to operate in the open base? Means open base means basically I mean, when you because you when you I mean basically um, um, see the point is maybe your means your I could think of means I don't know from means basically to change this transient, right? How quickly you could remove, how quickly you could put electrons in the base. If you keep the base open, that may help, right?
So, sir, it was like we were told that the base current will then act like a trigger. So, whenever we inject current in the base, then the BJT will conduct and circuit will be closed. Otherwise, it will be open. But
Right? It's the same thing, right? What this is the same thing I'm telling, right? See, the moment you forward bias to the junction, right? That means, see, you means you will see in the books it writes in different ways, right? So, you think a BJT is a device, it can act as a voltage control current source. That means you could give VB, right? I mean, you could VB to turn on the device, right? You could also force IB to turn on the device, right? You could do in both the ways, right? So it can act as a current control. That means when you force IB, if you force current, right? You put some current in the base, right? So if you give IB, the transistor will turn on also, right? Or you give VB, right? Both way it will work, right? But that is the good thing about VB, that the good thing about BJT, that it can work as a current control device, also voltage control device, both, right? So you could turn on, turn off by injecting current or injecting and giving voltage across the junction, right?
so, sir, like I was asking that in this case, we are not applying any bias at the base, but
No,
still
in
the
this case the
it
base
is
is open. See, in this case the base is open, right? So what is happening, right? I started with that. Okay, let's say there is some electron flowing, right? Right. So these electrons may be one or two electrons, right? Let's say very few number of electrons. I have to start this process somehow, right? So let's see there are some electrons. If I go I'll do it again here. Um, so this is my emitter. This is base. Um, this is collector. Um, let's not put it inside. Okay, emitter, base, and collector. So base is open. That means base terminal is not existing. Think of base terminal is not existing, right? So this is something like this, right? So what I'm telling is my emitter is grounded. So I'm giving the voltage. This is my VC, right? This is my VC, right? Okay. So now, see, when I give some voltage, so definitely I'm applying positive voltage. This junction is reverse bias, right? But I don't know about this junction, right? Because I don't know what is the voltage in the base, right? I don't know whether this junction is forward bias or not. But if you see, means if you means as an electrical engineer, if you apply common sense, right? So this side is emitter, this side is collector. So this side is ground. I have a positive voltage this side. So base will have some positive voltage, right?
Yes.
Right. So what I'm telling is, I'm starting with that. Okay, let's say there is some electrons injected. There is some positive voltage in the base. So emitter base junction is little bit far biased. So there is some electrons injected here, right? Right. And these electrons will reach collector base junction alpha times of these electrons, the base transport factor times, right? Right.
Yes.
Since base is open, I could have alpha equal to alpha t, right? So right. So because there is no base current, so whatever electrons I inject, they will collect at time. So okay, let's say alpha t times of these electrons will reach collector base junction. This junction is reverse biased, right? These electrons will go across the junction, right? Okay. At the same time, I have also minority holes from collector to uh, base and minority electrons. So this is the electrons coming from the EB junction, right? These are the minority electrons going from base to emitter, and these are the minority holes coming from collector to base, right? So these are the three components which are going through my collector base junction. Is it clear?
Yes, sir.
Yeah. So that's the reason I wrote this. I wrote this, right? So that's why reason I wrote this. So my IC will be alpha T IX, because whatever electrons, let's say alpha T of those electrons reach collector base junction, plus ICBO, then they'll be multiplied, right? Because this is a this is a reverse bias junction, so they'll be multiplied. So IC will be m times alpha times Ix plus ICBO, right? Alpha T, right? Okay. So here again, so now because here I have electron hole pairs, because electron holes are going through this junction, so these electron holes will participate in the impact transition process, and they will create extra electron hole pairs, right? They will create extra electron hole pairs, right? And these electrons will go to the collector because there is a field from collector to emitter base, so electrons will go in the opposite direction of the field. So and holes will go to the base, but the holes will come to the base. But the moment the holes arrive in the base, they don't have anywhere to go because base is open, right? So if they don't have anywhere to go, so they'll be collected, right? So impact transition is happening. Holes are electron hole pairs are generated and holes are being collected, right? If you think from the time point of view, with time the number of holes in the base is increasing, right? So if the number of holes in the base is increasing, that means it will increase the potential of the base region, right? So it will increase the potential. If they increase the potential, that means this junction is forward biased now, right? So more electrons will be injected, right? This is how it will trigger. It's a positive feedback process, right? More electron, more impact transition, more holes, then again more electrons, right? So this is a positive feedback process, right? So this process will go on, go on, go on. At some point of time, your IC and I will be very high, right? And that is the breakdown voltage, right?
Yes.
Right. So here, I mean, here we are starting with some small electrons being injected from emitter to base, but that small electron is, because the positive feedback process is becoming very high with time, right?
Yes.
Like here we are considering that because of hole accumulation, forward biasing of EV junction is taking place. So since there is forward bias, so holes will also get injected to
That's the
emitter.
reason it is forward bias. So I need something about the holes to drain away from the. That's the reason hole itself makes it forward bias, so that it could go collected at the emitter. Means it could be injected to the emitter.
Yes, sir. So like as it will be injected to the emitter, so hole concentration will reduce.
Yeah, yeah,
So
yeah.
the forward bias will
Dynamic
also
process,
reduce
right?
now.
It's a dynamic process, right? Your electron hole is increasing and holes are being collected, because see holes, hole डाल दोगे भी तुम्हारा base में, the holes will not be there for a long time. Anyway, these holes will recover. Then holes will find some way to go away, right?
So the voltage भी it will also drop there. फिर
Yeah,
से
yeah, but it's a
accumulation
steady
तो वो
state process. See, steady state process देखोगे तो holes तो continuously आ रहा है collector base junction से, right? In the steady state, so your base will be at some potential, right? Right. So that potential will go on increasing with right. See, holes are being injected to the base, they are collected and they are drained away, right, with time, right? But in this process, you will see there will be net amount of holes at any point of time in the base, right? In the steady state condition, right? So that net amount will increase the potential of the base and it will further bias the base emitter junction.
So here, like looking at a device, we cannot say like since there are multiple junctions and a device for breakdown will need to penetrate, like to break these many junctions. So how will it's?
Not about junctions, there is
Huh.
two junctions between collector and emitter, right? It's not a
Yes,
CV junction get will break, right?
yes,
But it is a different process, right? So the process is there is a positive feedback coming, right?
mm,
And because of that positive feedback, and this is that's see here your m doesn't become very high, your m alpha, right? So basically, so you only, so for a bbcbo to happen, your multiplication factor should become infinite, right? M becomes infinite, but here it is not necessary. Your m equal to 1, m 1 में हो जाता है, right? Breakdown, right? And this m 1 में हो जाता है क्योंकि there is a positive feedback coming into picture, right? So बहुत जल्दी breakdown हो जाता है, right? In case when the base is open, right? So because when the base is open, because holes are accumulated, these holes actually, these holes, because in the when we're talking about emitter open, these holes are injected and holes are being collected at the base, right? Means base contact, right? So there is no way holes are staying in the base, right? But here holes are staying in the base for some time, right? So that is creating so they are also taking part in the impact transition, right? Because they are increasing the base voltage and they are allowing more electrons to go from emitter to base, right? And these electrons are participating in the impact transition, and that is also creating an impact. So it is means adulterated, right? So if you compare BBCBO and BBCO, so if you think from the physics point of view, the BBCO will always be less than BBCBO, right?
yes, sir. So that is what I was saying. So by looking at a device, we cannot predict ki, like how will the breakdown be compared to some other device. It will basically depend on the physics of that device
Yeah, it will depend on
ultimately.
the design of that device, how that device is
Huh.
designed, right? That's the reason
Yes,
beta factor is coming into picture, right, in the equation, right?
yes, sir.
Right. So if you design a device, your beta is very low, right? Very poor.
Mm.
That means let's say you have lot of defects in the base, right? So holes are being injected, holes will defect तो come in defect में वो ये हो जाएगा, recombine हो जाएंगे, right?
Yes, sir.
Right. Then there is no way that it will create a positive feedback, right? Right. So if your beta of the device is very poor, beta, what do you mean by beta of a bipolar junction transistor? Beta something relates to the base part of the of your BJT, right? How well you design your base, right? If your base is very good, your beta will be very high. If your base is not very properly designed, your beta will be low, right? Right. Beta depends on the base width and the number of defects, the combination in the base region, right? This is IC by IB. IB depends on base width and recombination, right?
Yes, sir.
Right. So yeah. So if you design the device properly, for beta is very high, you will see that your BBCO means your positive feedback will be more, right? So
Yes.
your BBCO will be much more less than BBCO. If your beta is very low, then positive feedback to आने में time लगेगा, right? Because your holes has to accumulated. But if the beta is very low, then that means these holes are also unheated, means the holes
Mm.
are gone, right? So your BBCO will be very close to BBCBO if your beta is very bad, right?